Okay, I need your 83 and 84 if you did not turn those into Google Classroom. 83 was the worksheet 1, worksheet 2, and 84 was the short worksheet that was called Extra Practice. Make sure you've got both of those, and then clear your desk off. Phones and smartwatches need to be put up, and then I will let you start your quiz. There's a little one right there. Table and a graph, and the table's worth a point and the graph's worth a point. So I think that totals up to 26 points total. All right, did I miss anybody?
address?
No. I'll update it. Thank
Where's
you.
Where's 83 or 84?
84 will be over there in the basket that says Pigman.
I turned in the 3.1 and 3.2 stuff online, but he's giving me zeros for it.
Yeah, no, I sent you an email. There was nothing attached.
There wasn't?
I don't know either one of them.
The pictures didn't upload. Can I just show you the map? Okay, let me grab it.
See, both of them just look like this.
Oh, I'm
no,
sorry.
No, it's fine.
Here's 84.
Okay, that's good.
And then the front and back of 83.
Okay, that's it.
Thank you.
Oh, yeah, put them in the basket, please. In 5 minutes, we need to move on. So if you're still working, you need to finish up in the next 5 minutes. Okay, if you're still working, you need to finish that up and get it turned in. And the rest of us, let's go ahead and move on. So we're moving on to section 3.2 today. This is the two handouts you picked up. We've got a short one that's focused on graphing, which is number 86. And then a longer one that'll make up 87. Now, of course, inverse functions are important, or we wouldn't spend class time on them. Exponential functions are important, or else we wouldn't spend class time on them. But just to give you a heads up here, our next 3 sections will be 3.2, then 3.3, then 3.4. All 3 of those sections are about logarithms. So the stuff that we're gonna go over on these 2 handouts, a lot of this is gonna carry over for the next several weeks. So you certainly don't want to start off feeling like you're behind. Okay, so on this one, this is the graphing one, and really it's just the first couple parts here that are a little bit different and something new. And then after that, it should be pretty consistent with what we've done in the past. So what you need to know new from this is that the relationship between log base 3 of x and 3 to the x, these two are inverses of each other. That's why we did inverse functions from chapter 1 and then jumped to chapter 3, so that made some context to you. Also, log base 8 of x and 8 to the x are also inverses. So we will ask you, what do you think the inverse of 5 to the x is? And you will need to tell us it is log base 5 of x. Or go in the other direction, what do you think the inverse of log base 2 to the x is? And that would be 2 to the x. So we usually put that on a quiz and or test as a question or two. But you need to know that relationship. But really the reason you need to know that relationship is not so that you have it memorized and you can get 1 point on a quiz and a couple points on a test. It's because it's really meant to help you graph something like question H. Without a calculator, if I asked you to graph this, I think very few people would know how to do that from Algebra 2. But imagine if we started off graphing 2 to the x, which is what we just talked about, exponential functions. So 2 to the 0, 2 to the first, 2 squared, 2 to the third, and his exponential growth. And the reason why you might start with that one is because 2 to the x and log base 2 to the x are inverse functions. And all it means to be an inverse function is you switch x and y. So 0, 1 becomes 1, 0, 1, 2 becomes 2, 1, 2, 4 becomes 4, 2. Just keep switching x and y for all of these points that you have. And then you know what log base 2 to the x looks like. Now, it's not really important right now, but notice this line of symmetry at y equals x also. So there's our visual confirmation that those are inverses of each other. Well, if you can graph this one, which I hope you can, because we just quizzed over stuff like that, and you know what it means to be an inverse function, so you switch x and y and replot your points, then the only thing keeping you from graphing number 6 is your transformation rules. Adding directly to 3 is going to make you go left 3. So take all these points we were sure about, move them left 3, and replot them. And that's how you should inch yourself towards graphing something like log base 2 of x plus 3. Realizing that log base 2 is the inverse of 2 to the x. If it helps you to actually sketch 2 to the x, just do it. Switch x and y to get log base 2 to the x because this is inverse, and then apply the transformation, or transformations plural. Now, when you do have more than one graph on your paper, just so you guys know in mathematics, you do need to label these. So like, if you don't tell me what is what, I can't assume that the correct one is your answer. You need to say, at the very least, if you were asked to graph this, at least call him h of x. If not, also label these. But don't have multiple graphs on your page and not say what they are. Okay, so one more example of that, because normally, if you needed to graph something like this, you're not going to have this hint of start with this, and then think about how this is different, and then think about how this is different. Normally, it's going to look like question 7. Here's a logarithmic graph. We want you to be able to graph it, and then maybe answer a couple characteristics about it. So when I look through all of this mess, I would say this would look like log base 3 with some transformations. And I know log base 3 is the inverse of 3 to the x. So I'm personally going to graph 3 to the x, because it only takes me 2 seconds anyway. I'm going to take those points, switch x and y, and then I'm going to have log base 3 to the x. And then I can worry about the transformations. It looks like if you plug the number in for x, the first thing you would do is add 5 to it. So the first transformation is going to be left 5. So all of these points need to move left 5. Then it looks like the next transformation would be this negative. And where that negative is, that is going to reflect over the x-axis. So points on the x-axis stay on the x-axis. Other points will flip over. Now, maybe not for you, but for me, my graph is starting to get a little bit too busy. So I would erase some of my previous steps, stuff that I just don't need anymore. I prefer that. If that doesn't bug you, then you don't have to keep up with them, I guess. But and then finally, this last piece would be down 1. So shift all these points down 1. And then either erase all the previous stuff, or at least label this guy as I of x, since that was his name. So you need to know your transformation rules for other stuff anyway. From the top of this worksheet, you need to know the connection between log base 3 to the x and 3 to the x. And so I guess it's kind of broken up into a bunch of steps, but that would be the process to doing that. And of course, once you have the graph in front of you, then answering characteristics about it should be pretty easy. So like the domain, looks like he goes as far left as -5, but doesn't quite reach it, and then goes forever to the right. The x-intercept is right here at about -4 point something. We have to know a little bit more about logarithms to solve for that exact value, but for right now, we're going to just stick with that. And then these graphs will have a vertical asymptote. So this vertical asymptote is the vertical line, and because it's a vertical line, it's going to be x equals. It's going to be the vertical line that it approaches but does not cross. So -5. So we'll practice some more graphing later on, but again, really the only thing completely new is the first couple questions. Understanding that relationship, and then if you know what you need to know about transformation rules, you know what you need to know about exponential functions. If you know what it means to be an inverse function, then you already have the rest of the pieces. Okay, anything that jumps out at you at this handout? Okay, then let's move on to the longer handout. So this is some of the logarithm properties, and to help show you why these are needed and what they're really meant to do. So if I ask you a question like this one, you should be able to answer this pretty easily. 2 to what power gives you 4? That's going to be 2. 2 squared gives you 4. But then I ask you something like, well, 2 to what power gives you 5? And all of a sudden, that's not such an easy question, because that's not a nice whole number. But when exponential functions just show up naturally a lot, lots of real world scientific type stuff, we've got to be able to solve for that sometimes. So we're going to come back to that in just a second. In fact, right here, we'll come back to that. So one thing that you need to be able to do, and I know you guys saw this in Algebra 2, this is also big on the ACT, but you need to be able to go from exponential form, which is what these 4 are written in, into logarithmic form. So the way I do that is logarithmic form is going to have the word log in it, and to switch the forms, you just have to switch 2 of these things. So for this one, it would be the 2 and the 9. So 3 squared equals 9 is the same thing as saying log base 3 of 9 equals 2. I just switched the 2 and the 9 and put the word log in front. Switch the B and the C and put the word log out front. Switch the 2 and the 16 and put the word log out front. And then sometimes when you do that, like this one, when you switch the x and the 5, I just solved that. That is the exact answer. Log base 2 of 5. And I will show you in a bit how to estimate that if you needed a decimal. But it's about that. So sometimes just switching from exponential form to logarithmic form is all that needs to be done to solve an exponential equation. So if it's something that's nice and even, great, do it in your head. But a lot of times they're not going to be nice and even, especially in the real world. So sometimes this is where logarithms start to be needed. Now, if you can go in this direction, then you should be able to undo it, which is the next thing. Go from logarithmic form to exponential form. So basically, I just want to not be in logarithmic form, but to remove that, I need to switch these 2 things back the way they originally were. You're switching the same 2 things that you would switch in the other one. So this one would say 3 squared is x, or a to the b is c, or 8 to the x is 11, or 2 squared is 4. That sounds familiar from Algebra 2? You remember doing that some? Okay, you also need to know, like if you're looking at your calculator, it's got two buttons that it gives specifically to logarithms, if that's a sign of how important logarithms are. It's got a log button, but it doesn't let you put a base in. This is called the common log. And then there's this ln button that stands for natural log. I don't know why it's L and then N and not N and L, but natural log and common log. Those are the only two that your calculator has pre-programmed in. You need to know that natural log just means log base e. These are saying the exact same thing. They just look different. Natural log means log base e. Different way to make it look. And until you're more comfortable with natural log, you should always just write it that way so that you can see it. And this is the same e that we talked about recently, the 2.718 number, the one that comes up in the compound interest formulas and such. If it does not have a base written, it's the common log, and that's assumed base 10. So until you're comfortable with that, anytime there's not a base there, I would just write in a 10, and then you don't have to worry about it being any harder. But natural log, base e, no log listed, it's understood base 10. Okay, we're going to look at some easier questions on how to evaluate a logarithm. So basically this just means how to read it. And on the first one, I'm going to go through kind of the longer process, which I don't normally do. But I think it's good for you to see it once because it is a fair strategy. Let's say I want to know what this is equal to. Well, let's just set it equal to x for just a second. And so x is my answer. If I can solve for x equals, then I know what this is. Well, right now, the only thing I've told you about solving logarithms is sometimes I said switching the form works. So this is currently in logarithmic form. And if I switch these two, I could put it in exponential form. These are saying the same thing, they just look different. This one is not as comfortable to us in our head just because we don't work with logarithms all the time. But this one, 7 to what power gives you 7? That's a lot easier to do in your head. So the answer to that question is just 1. So feel free to make it set equal to x, switch the forms, and sometimes that can help you. But what I do is I typically just phrase it in my head this way. I know this is saying 10 to what power gives me 100. I don't usually write this out, but that would be 2. Be careful, it's not 10 times what gives you 100, it's 10 to what power gives you 100. And even students who know that still slip up sometimes, so be careful. Again, no base written, so this is saying 10 to what power gives you 10, so that would be 1. This is saying 10 to what power gives you 1, that would be 0. Anything to the 0 power is 1. I'm going to do these kind of out of order. This question here, e to the 0 gives you 1. Anything to the 0 power gives you 1. These are kind of the same question. They're testing the same thing. Okay, this one is not 9. It's not 3 times what gives you 27. It's 3 to what power gives you 27. So 3 to the third. If the natural log bugs you, again, just squeeze in an extra step and make it log base e. All this is saying is e to what power gives you e. And then this one you got to be a little careful on because you got to use some exponent rules. 2 to the first would be 2. And then 2 to the negative 1, remember with exponent rules, a negative exponent in the numerator is the same as moving it to the denominator and making it a positive exponent. So 2 to the negative 1 is how you get a 1/2. So no need for a calculator on those. We just have to know how to read those, and those are usually pretty quick. Of course, you know, I think this one's just a tiny bit harder, but it's only harder because of exponent rules, not because of logarithms. Okay, I'm guessing you did a little bit of this in Algebra 2 also.
A
little bit? Okay. Okay. And then sometimes, like on the front page, I use my calculator for just a second to round something. So these don't come out the nice whole numbers, so we wouldn't expect you to do this without a calculator. This would be, well, I know 3 to the first is only 3, and I know 3 squared is 9, and 7 is somewhere between 3 and 9. So I know my answer is somewhere between 1 and 2. But if I need to represent that as a decimal, if I need to be more accurate than just between 1 and 2, we've got to have a way to type this in our calculator. And of course, some people have different calculators and stuff, but generally speaking, most calculators don't let you put the base in. You can do base 10 if you hit the log button, or you can do base E if you hit the natural log button. But they don't just let you just type in base 3. So there is something called change of base, and I'll be honest that this is a little bit outdated because a lot of calculators can do this now, and I will show you how to put this in depending on the calculator you have. However, we still ask that you learn this because there are a few calculus topics that you'll see that we prove with change of base. Change of base, I believe, still shows up on the ACT, and I know change of base still shows up in college algebra. So even though some calculators are starting to do this, you still need to be familiar with this. Okay, so change of base just says if you want to evaluate log base 3 of 7, you could either do log base 10 of 7 over log base 10 of 3, and that's good because my calculator can do base 10. And you could do natural log of 7 over natural log of 3. Both of those give us the same thing. And I will type both in to show you, to convince you. There's change of base with the common log. And there's change of base with the natural log. Exactly the same thing. I knew my answer was between 1 and 2, but now I can get more specific, about 1.771. Approximately. Now, even though either one of these work, in the past we have made these multiple choice, so you do need to know both. We might write the answer that looks like this, and if you only memorize this, you may get stuck. Okay, so what about my answer on this one? My answer is going to be between what two integers? Okay, since 5 squared is not quite enough, and 5 to the third is too much, I agree. Your answer is going to be between 2 and 3, but the way you can get your calculator to tell you is you could do log base 10 of 27 over log base 10 of 5, or natural log of 27 over natural log of 5. Both of those are considered change of base. It actually doesn't matter which base you use, it's just that 10 and E are the ones that are programmed in our calculators. Okay, and I'm going to type both in just to fully convince you that it doesn't matter which way you use it. About 2.048. I knew our answer was somewhere between 2 and 3. And the fact that 27 is way closer to 25 than it is to 125 means I knew my answer was closer to 2. But that's how you go about that. So this is considered the change of base. And at some point I'll show you how you can type it in just like that, just like it looks. But okay, moving along here. So the most important, I don't know why this is a duplicate here, but one of the most important properties about logarithms is this one. This is what makes them kind of unique and solve some questions that you can't normally solve. So what about this question that makes it where normal algebra stuff isn't going to work is what you're solving for is stuffed up in the exponent somewhere. You're basically trying to solve an exponential equation. But logarithms, if you have an exponent on something that you're taking the log of, this property of logarithm says you can bring that exponent down out front. Why that is good for this question type that we're going to see over the next couple weeks is you could take the log of both sides That's fair and balanced because I did it to both sides. And then this side matches this property. Now x plus 2 is an exponent on something I'm taking the log of. So x plus 2 can come down out front. That's the only algebra trick that we have to get something out of the exponent like that. Is to make it a logarithm and then apply the property that if it's an exponent on something you're taking the log of, bring it down. And then to finish solving this, I mean, these are kind of funny looking, unusual answers here, but we could distribute this. Two natural log of 4 is just a number, so I'm going to subtract it over. And natural log of 4 is just a number, so I'm going to divide it over. And then that would be our exact answer. So I'm not doing anything too complicated, especially considering how messy the answer looks. But if you don't know this property about logarithms, if you don't know that they're how you bring that exponent down, then you're pretty much stuck at the beginning. And I'm going to take just a second here to actually type this in. And store it. Okay, so this is what I think the answer is. So I don't know why you need a decimal, but I just wanted to show you that even though the answer looks very complex and you might think that there's no chance you could have an answer that looks like this, what this was supposed to solve was 4 to the power of x plus 2 is supposed to equal 6. So if I told my calculator this is what I think x is, it's not just close to 6, it's exactly 6. So you have to get over your answer looking super messy. It's perfectly fine. But taking the natural log of both sides, we'll practice that quite a bit more, but I need you to understand why this property is important. This is what makes logarithms useful and why we spend so much time learning them. Okay, there's another property that you need to be aware of, although you won't have to use it too much in here. And for years and years and years, I used to just show this to students and say, here's the answer, learn it from pattern recognition, and until you get to calculus, actually yesterday was the first time that they used this, you're not going to have a use for it, but we still expect y'all to know it. But this year, or last couple of years, I guess, I'm putting an example in here so you can see why you need to know it. So another property says if you have a number whose exponent is a log and it's the base of some number of something, all of that just simplifies to be the something. So let's maybe write out a few examples. 3 to the log base 3 of 7 is just going to be 7. As long as this number and this number are the same, it's going to simplify to be what you're taking the log of. So we will want you to be able to do questions like that. But again, truthfully, it's just a little bit pattern recognition. The reason why you need to know this for calculus is sometimes we want to be able to solve this, go from natural log equals to just y equals. And while you might think you can just divide both sides by natural log, it doesn't work that way because this isn't natural log times y, it's natural log of y. JP, you want to put your phone up? So there is a trick, which again, you're not going to be responsible in here for, but it's good for you to see it. So that's not completely new in calculus. But you can actually make this whole left side be an exponent on e if you're willing to make the whole right side be an exponent on e. And while you might think, why in the world would you do that? It's because then this property applied here, e to the log base e of y, just becomes y. That's really the only way to dig a y out of a natural log like that. So again, we won't test you over this part, but I'm just giving you some context of why that property is expected to be known. You probably saw that in Algebra 2 also, but you may not remember it because you didn't do anything with it. Okay, moving on. So we're getting pretty close here, but so evaluating some properties, some logs with using exponent rules. So this is like what I did on the front, but this is saying like 10 to what power gives you 1 over 10 to the 5th. That's kind of hard to do. So instead, rewrite this. A negative exponent in the denominator is the same thing as a positive exponent in the numerator. That's a little bit uncomfortable because in mathematics, 99% of the time we take a negative exponent and make it positive. But in this case, I want to move it up and make it negative. And the reason why I want to do that is now negative 5 is an exponent on something I'm taking the log of. Log base 10 of 10 would just be 1 because 10 to the first gives you 10. And so your answer comes from negative 5 times 1. So on the harder questions, you have to rewrite with exponent rules. So let's look at 3 more of those. Remember, natural log just means log base e. So if that bugs you, you can change that. And then instead of calling this 1 over e to the 7th, I'm going to call it e to the negative 7th. Now this is an exponent on something that I'm taking the log of. And I'm left with negative 7 times 1. This is 1 because e to the first gives you e. Now, if you have more than one term when you do this, if I want to move all of this up, it's not just the first term that becomes negative, it's the whole thing becomes negative. So now it's a negative x and a plus 1. But all of this can come down out front. Log base 10 of 10 is 1. So you were left with negative x plus 1 times 1. If you move all of this up, make sure you don't just make the 3x negative, but also the plus 2 negative. Now it's an exponent on something I'm taking the log of, so all of this can come down out of the exponent. Log base e of e is still 1. You're going to get sick of hearing that one because it comes up a lot. But these are not equations. We're not solving for x. We're just trying to simplify. Okay, I know we talked about graphing on the other page. So to graph this, I think we may have done this exact function, but I may have graphed 3 to the x and then switched a bunch of points to get log base 3 to the x. But just like 2 to the x looks like 3 to the x, looks like 5 to the x, looks like e to the x, that means the inverses are going to basically look the same too. Whether it's log base 3 of x, log base 5 of x, log base e to the x, they all basically look the same. They all have a x-intercept of 1. They all have the same domain. They all have a vertical asymptote at right here at x equals 0. Just like exponential functions are basically the same, these are basically the same. All that changes is how quickly this one shoots to the right and how quickly they hug up to the y-axis. But quick sketch, all logarithmic functions, if you don't have any transformations, basically look the same. So if we pull this guy down, he has a vertical asymptote right here. The vertical line, which makes it x equals, that he approaches but doesn't cross. Now, if I shift my graph left 4, this would be left 4, then the whole graph shifts left 4. So also, the vertical asymptote gets shifted left 4. And of course you could sketch it if you're willing to spend a bunch of time on it to see that that's where it is. The two that I'm worried about are these two, because you may not have ever heard this before. So I know log base 3 to the x has a vertical asymptote at x equals 0. Oh, we missed one here, but it's fine. It looks the same. So if it shifts left 4, the vertical asymptote moves left 4. So we're trying to think about these transformations. So when we do this, this flips it over the y-axis. If you only multiply x by a negative, you flip it over the y-axis. So here's what log base 3 of x looks like. If I flip it over the y-axis, this is what log base 3 of negative x looks like. And then here's the part that I'm concerned about, that I think you probably didn't hear in Algebra 2. But this, when you add to x, you're used to that being left 4. However, if you're reflecting over the y-axis, those rules switch, because it's really like this. The negative is not really just going to the x, it's also going to that 4. So this is actually right 4. So if it was at x equals 0 and then I shift it right 4, it's now at x equals 4. But the rules for left and right transformations are backwards if you're flipping over the y-axis. So on this one, natural log of x would have a vertical asymptote at x equals 0. If you flip them over the y-axis, the vertical asymptote is still at x equals 0. And then normally this would mean shift left, but since I reflected over the y-axis, this is actually shift right. So if I move this whole thing right 7, the vertical asymptote is going to move 7. And again, I'm sure your teachers, algebra teachers, if they did talk about it, didn't come up much, but I would probably write that out in words. We have quizzed on that in the past. Okay, I'll give you a second to do that. Okay, and then to finish up, so we will have you start to solve some equations, but we really get deep into solving equations in section 3.4. 3.4 is the last section of logarithms that we do, and it's all about solving equations. That's the only thing you do in 3.4. But in the meantime, we have some easier ones kind of set up for you. But you do need to be aware that with logarithms, sometimes you have extraneous solutions. So it's okay to have a negative answer, it's okay to have a 0 answer, but it is not okay, it's not possible to take the log of a negative number or 0. I don't know why that's not typed out, but you need to write that in. You can't take the log of a negative number, you can't take the log of 0. And just quickly, why? This would mean 2 to what power gives you negative 1? And there's no number that makes that true. If you think about the graph 2 to the x, he never equals negative 1. He also never equals 0. He gets close to 0, but he never equals 0. You can't take the log of a negative, you can't take the log of 0. Okay, so if we start solving these, this is log base 3 of some stuff, and this is log base 3 of some stuff. So the log base 3 part's already balanced out. We just need to make sure that the stuff, the inside stuff, is also equal. So take away an x from both sides, take away a 5 from both sides, you get this as an answer. And some people will say that this is not the answer because it's negative. It's okay to have a negative answer. It is not okay to take the log of a negative number. So you actually have to go up here and plug it in and see that if you plugged it in on the left, you're taking the log of a positive number. On the right, you're taking the log of a positive number, and you can see that the left and the right are the same. So then you can be confirmed. Okay, over here, same thing, log base 3, that part's already balanced out. So we just need to make sure that we're taking the log of the same thing. So set the insides equal to each other. This is a quadratic, so I would put everything on one side set equal to 0. Hope that it factors, because that's the easiest way. And I think I get an answer of 1 and -3. But one of these may not work. Maybe neither of these work. They could be extraneous. Extraneous means I didn't do anything wrong and my math logic is fine. It's just that just because this solves this step, which is a representation of this step, which is a representation of this step, which is a representation of this step. Right here, what we did for convenience, like we're pretending like it's not a log question for just a second, but it really is. So to be sure that those are correct, you would want to plug in 1 into the original problem, and you would get this. And even though it makes the left side equal to right side, this is not possible. You can't, there's no exponent of 3 that gives you -2. So that is extraneous. It would be incorrect to leave it as an answer. If I plug in -3, not only does the left and the right side equal each other, but I'm not taking the log of 0 and I'm not taking the log of a negative. There is some power of 3 that gives me 6. It's not a nice whole number, but it at least exists. So there's only one answer there. So when solving logarithmic equations, we will have to train ourselves to plug them in and make sure that they work, because sometimes our algebra is going to create answers that don't really solve the original problem. Okay, so I realize that there should be a few things new in here, probably like this y-axis reflections, switching the horizontal transformation rules. You probably need to mark that up. I think these questions are a little bit harder using the exponent rules. So I don't have any specific homework for you guys, but if you don't remember this from last year, evaluating these basic ones without a calculator, if you don't remember switching from logarithmic form to exponential form or exponential form to logarithmic form, I would spend maybe just 5 minutes scanning through this before our next class, just so that all of it's kind of fresh in your head, because we're going to be using a lot of these things. So you don't have to have it mastered by next class, but the sooner you're more familiar with these, the easier things will go for you. And we are on, I don't know, I feel like our schedule has been kind of cheating us quite a bit here, but since there was no school on Monday and this week is a B week, I will not see you guys again until next Monday. So asking you to look that over for a quick 5 minutes should be pretty manageable. But I guess if you don't remember any of it, you might spend a little bit longer.